Thank you, Ed. We have some people that are being supported by this group that are outside of the church that can't attend, or they're for whatever reason they're not able to attend. I would like to get a count this morning. If you have somebody that's outside the church that you're getting the handouts to, or that you're supporting through this process, that you've gotten a notebook for them, would you raise your hand? Tell me how many people you have. Roy, I know you've got 2. And any others? Okay. All right. So I was reading through a survey the other day. I've been reading through several surveys, but I came across this one, which is, our question: does God exist? And the question was presented to a large group of self-proclaimed Christians. These are people of all ages, 18 and above, that proclaim to be Christians, that have a strong Christian faith, or that have a Christian faith. And they were asked this question: have you, or do you now have, doubts about God? And that was the question that was presented to them. Well, the way they answered, 26% said that they have had doubts and they still have doubts. These are believing Christians. 40% said they once doubted, but they've resolved their doubts and they're good to go. 34% said they've never doubted at all. And so this is, of believing Christians, 66% at least at one time in their life have doubted whether God exists or not. And I thought that was a fascinating number, and it's directly related to what our study is about here. So 66% of people in the church, in the church corporate, have had doubts about God's existence before in the past. And so I thought that was interesting, and I wanted to bring that forward to you. Just real quickly, we got into the next lesson a little bit last week. I want to give us a quick summary, and we'll get started again. But we started off saying we're going to look at the 2 different forms of revelation that God's given to mankind, one through Scripture and one through nature. We began with the cosmological argument for the existence of God by looking at the cosmos. And from that argument, we were able to come away that yes, there's a first cause, that there's something that caused the universe to exist, and that the universe hadn't been here forever, it hadn't existed forever, and so there is a first cause that created that. And so that drove us to ask the question, okay, there's a first cause that created the universe, but how did He create? And what did He create? Not specifically He created, tigers and bears and humans and plants and trees. Not specifically like that, but how did He create those things? How are those things made up? How are those things constituted? How can we deconstruct those things or reverse engineer those things to see how they were made up? And so that was the question that came out of the Kalam cosmological argument. There is a first cause that caused the creation of the universe. So now this next step, what can we do to learn more about that? So let me get us caught up on our slides real quick. We talked about if you're going to study a painter and you want to know more about the painter, you look at his artwork. If you want to know more about a person that hand forges knives, then you look at their knives and you can tell something about that person. If you look at the universe, we should be able to tell something more about God. We had said there was a man named William Paley. William Paley had said that there are things that we see in the world that just indicate to us that they're designed. If you walk through the woods and you see a rock, then it's just a rock and that's no big deal. But if you walk through the woods and you see a watch, then that watch says that there's some designer that created that, there's intentionality. And so we talked about this central question that we're asking, and we're providing all this evidence toward this central question, or this central truth, and that statement is that God exists and Christianity is true. And so now we're going to get into the teleological argument, and we're going to present more evidence toward that same argument. And so we said that there is a creator. And so the premise of the teleological argument is another very simple argument. You could say every design had a designer. We know that. Any of you that are artists, you know there has to be a designer that designs something. If you build houses, anything you build or do, anything that has a design has to have a designer. The universe is a highly complex design. And so therefore the universe had a designer, and now our goal is to prove those first two theses, or those first two premises, to prove the last one. And so I want to start out with the four primary forces. Now, this is where we left off last week, and this is probably one of the hardest lessons that there is to kind of visualize as we go through. If you miss part of this, don't worry about it. It's not a big deal. It's just the overall idea of it. This gets much better, but the teleological argument is actually two different arguments in one. There's an argument from the cosmos, you know, from the stars and the moon and the planets and their rotations and all of that. All the Big Bang stuff we talked about and how all of that works. And so there's that argument. And then there's the design argument, or the intelligent design argument, is really more focused upon biological systems, the design that we see in human beings and design that we see in animals. So we're going to look briefly at the cosmos, and we're going to look at the design that we see there, and then we'll move on to the design that we see in biological systems. These are huge topics, and I'm just barely going to scratch over the surface. But we want to start. So the first force that we can look at is the strong nuclear force. And this has to do with atoms. And we talked a little bit about atoms last week. The strong nuclear force governs how tightly protons and neutrons are held together. That's the cluster of the little balls in the center of the picture there. Those are the pluses are the protons, the blue ones are neutrons. And those are held together and stuck together by these strong nuclear forces. If that wasn't the case and they weren't held together, if that force was any weaker, those wouldn't hold together, and you would end up with all the atoms that we have in the world would just have one proton. And one proton would be hydrogen, and so there would be nothing in the world but hydrogen. And that's a very narrow range that those fall in. If that force was too strong, by even a slight amount, then the protons and neutrons it would take too much for them to pull apart, and there would be no lone protons, which means there'd be no hydrogen. So in one way you have only hydrogen, another way you have no hydrogen, and either way you can't live in a world, in an atmosphere that doesn't have hydrogen. You can't live in a pure hydrogen world. We wouldn't even be constituted. You can't live in a world that has too little hydrogen. So this is a delicate balance. And it's a very, very delicate balance that we go through. If it was 2% weaker or 0.3% stronger, no life would be possible. That's how tight and how narrow that is, those forces inside those atoms that make up everything. The second force that we're going to touch on briefly is the weak nuclear force. The weak nuclear force also governs how atoms hold together, and they are directly related to radioactive decay. And so most all elements have a radioactive isotope or a radioactive sister or cousin, you might say, and they degrade into other components. And that rate of the radioactive decay is very important in the production of other elements that are needed, other chemistries that are needed for life to be supported. If this weak force were very much stronger than it is, then the matter in the universe would quickly all be converted to heavy elements. And the heavy elements like, the metals like lead and copper and things like that. If the weak force was very much weaker, only the lightest elements would occur in the universe. And so it's very much like the strong nuclear force as well. But the point here is that if it was slightly stronger or slightly weaker, we would end up with either very, very heavy atoms or very, very light atoms. And you can't make human beings out of lead or bismuth, and you can't make them out of hydrogen or helium. So you have to have all those intermediate atoms that we have. The next force is the gravitational force. And gravitation is responsible for the rotation of the planets, how they stay in orbit, and how they stay perfectly in orbit as they rotate around. But it's also responsible for stellar burning rates. The rate at which the sun burns is part of the gravitational forces. If the gravitation moves one way or the other, the rate that the sun burns goes crazy. And it either burns out too quickly, we get too hot, we can't live here, or it burns too slow and we freeze to death and we're in another super ice age. And so, like all the other these force constants, the gravitational force has a very, very tight range. And by that range is 1 times 10 to the minus 38th. And that's a scientific notation because there's so many zeros. If it varies by that much of a percent, we wouldn't be here. That's how tight these parameters are. That's a 0 with 38 zeros and a 1. If you change that gravitational force by that much, we're not here. The heavens declare the glory of God, right? The fourth force is the electromagnetic force. This is also a force that's concerned with chemical bonding and the production of the right chemistries that we need for life. And here again, they're in a very tight range, and we have to stay within that range, and we have to stay in that range from moment to moment to moment. We can't vary off that range very far at all, or we get in big trouble. But I want to talk about the expansion of the universe. We talked about that in the Coulomb cosmological argument. If you remember, we said that the universe is expanding, and they know that by looking at the red shift. You remember the light that comes from the stars, and it's moved, the red light has moved a particular distance along the spectrum of light, and scientists can measure how far that red light has shifted, and by that they know how far away the star is and how fast it's traveling. And from all of that, they say the universe is expanding, which means it came from a very tiny little beginning. Scientists call that very tiny little beginning the initial singularity. The initial singularity is what Christians call let there be light. And so that very initial singularity where everything is in a tiny, very, very small, dense, tiny, finite speck, an initial singularity, God declares and decrees let there be light, and that begins the whole process. That expansion rate is very critical, and that expansion rate was set at the instant God says let there be light. So it starts to take off with a particular velocity. Like you shoot a gun, the bullet comes out at a particular velocity. The velocity that the universe began to expand with is very, very specific. It's very, very tight. It's a very, very narrow range that it began to expand. And the reason it has to be in this tight, narrow band is if it's expanding too fast, then it ends up collapsing and falling back in upon itself. If it's expanding too slowly, it collapses back in upon itself. If it's expanding too fast, then you can't form stars and planets as it goes along like it did. This expansion rate is an even smaller number. The expansion rate of the universe is 1 times 10 to the minus 55th. It's that much. The expansion rate, the rate at which the universe is continuing to expand, if it's changed by that little percentage there, we're not here, or we wouldn't be here. If the initial singularity, that initial expansion rate had been off by that much, the world wouldn't have come into being. And so there are several of these, and I want to pass these out. I'm going to ask somebody to come help me with this. Pass some of these out. Let y'all pass those along. So I'd said last week that I would, this is what I was looking for. I was given a lesson, a Bible lesson one time, a class, and I got through it, and people were coming through and talking about it, and this man came up. He was a teacher, retired teacher. And he said, a great lesson, but one pointer, you never chew gum when you're giving a class. So I've been hunting for my paper, and I just found it. It was on the floor, so no gum. So we presented 4 of the force constants, the first 4 on that list. I told you last week that I'd try to find that list. There's 35. There's many, many more that haven't been discovered yet. But here's 35 different parameters. There's 35 different ranges that things have to fall in exactly, or the universe wouldn't be here. Thank you. Appreciate it. That's good. And so let you look through some of those. Look just real quick and see if any catches our eye. But we covered the first 4 because they dealt with atoms, and atoms is what everything is made of. Anyway, entropy levels, and number 9. That has a lot to do with why evolution can't be true. The theory around evolution, entropy is disorder. And the disorder level of the universe has to be within a very, very tight range. Some of these things don't make much sense, but the radiation, the initial radiation after creation in the universe, they call that the background radiation. The decay rate of beryllium, all of these decay rates that make other elements. But you could just look through there, though, and like I said, there's many. There's 35 of those different parameters, and like I said, there's many more. And if any of those are off by the slightest amount, then the universe doesn't come into existence. But fine-tuning happens also in the biological world. This is an electron microscope photograph of mitochondria. Mitochondria are intercellular little organisms, little organs inside cells, and this is the powerhouse. This is where ATP production takes place, and where we get our energy ultimately is inside the mitochondria. And if you remember, I preached a sermon several months ago about the you can go back to mitochondrial Eve through DNA, through genetic studies. That mitochondria, the DNA in mitochondria is passed from mother to daughter to mother to daughter, mother to daughter. And you can do a lot of neat genetic studies based on mitochondria. Anyway, there's a lot of design in nature and in biological systems. In 1859, Charles Darwin kind of blew the world up when he released his theory of evolution in his book called On the Origin of Species. He caused quite a stink and continues to cause quite a stink as well. But his model was based upon what he said were that there were some primordial cells. There were some ancient, antiquated cells, and that these cells began to mutate. And these mutations, through natural selection over millions and millions of years, we ended up human beings. They say, from goo to you via the zoo. If you've ever heard that before. It's kind of one way to remember it. So, but for Darwin's theory to work, there must be a genetic mutation that's a benefit to the organism, and that helps its survivability. If you'll look in your notes, your outline this week, that's on page 4 in that first or second paragraph, and I wish you'd underline that, because this is the basis around Darwin's theory, and this is the theory that we argue against, we counter-argue. Darwin's theory, for it to work, there must be a genetic mutation that is a benefit to the organism that helps its survivability. And then that mutation is carried on and improved and carried on and improved and carried on and improved. So let's say there's a fish, and all of a sudden there's a little fish born with 2 little bumps on his sides here. His little fins don't really work like fins. They look kind of weird. And then his children, they get a little bit longer, and then his children, they get a little longer, and then his children, they have fingers, and then they pull themselves out on land, and then another mutation in their back legs, on and on and on and on. All those steps to get to human beings. And that's what Darwin's theory is, and that's how it changes. He looked at these beaks of birds, and he saw all the different types of beaks, and he said, you know, this is the same kind of bird. It's got all these different beaks. They're in the process of evolving and changing. Well, we know now that that's environment. You know, the bird with the huge beak is eating a berry that has a really hard shell on it, and so, you know, he's adapted to open that shell up. But he hadn't gone from a bird to a human being. You know, and that's what Darwin is trying to argue. So that's the key to it. And so here's an example of what Darwin would have you believe. This is how an eye came about in evolutionary theory. That at some point there was some glob of goo, and it began to have these photosensitive cells right at the surface of its goo, where it could distinguish between light and dark. It couldn't see, but it could tell if it was a little bit light or if it was dark, and those were photoreceptive cells. And this sprung up just by genetic mutation. Then in the next step there, it began to draw back into the skull and make this empty pocket. And then it began to close off even more. Then the bottom left, it closed off and started to form the retina in the back of the eye. And then it formed a lens and a cornea, more and more genetic mutations that ended up being an advantage to the species. And then you see they eventually end up with an optic nerve, a retina with rods and cones, iris, all of that stuff. You know, the aperture of the lens, aqueous humor, all of that came into being, and now we can see. And that's how we got our eyes. And that's what evolution says. Through all these successive mutations from light-sensitive blob to our eyeball. That's what they would have you believe. So, interesting thing though, Darwin made a very interesting statement. Darwin said this: if it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous successive slight modifications, my theory would absolutely break down. You see, Darwin knew that this wasn't an airtight story. He left it open, you know, that someone might come back and say this is wrong. He didn't say this is absolute truth, this is absolute atheistic gospel. He didn't say that because he knew that someone could come along and say, you know, and prove that this isn't the way we developed, the way our eyes developed, you know, the way your dog's eyes developed. There was a man named Michael Behe. And in 1996, Michael Behe wrote a book called Darwin's Black Box, and Behe took up Darwin's challenge. And he said, I've got an answer for that. And he wrote this book, and he became hugely popular among Christians. He's received a lot of criticism from the other side, but you know you're getting to them when you get a lot of books written about you in a bad way. You know you're getting to them. So he wrote another book in, I think, 2005, and he answered all those. And his argument is still very, very solid. So bear with me. This is brand new, unopened, okay? Just so you know, these are mouse traps. I want you to take these and look at them, hand them around. You'll have to hand them back as you go. They're clean. So I want you to look at all the parts and pieces on that. I want you to see how it's built and how it's put together. And here's what Behe said. He said, if you look at that mousetrap, there's not one single part that you can remove. Not one part. Look at it that way. Is there one single part in that mousetrap that you could take out? The staples, the wood base, the catch, the hammer, the latch, the trigger, none of that. I looked and looked at it. There's nothing you can take away from that system, and it's still operating, it's still function. So that's a complete system. And that is what Michael Behe called an irreducibly complex system. Irreducible complexity is this. An irreducibly complex system is one which has many parts, and each part is necessary to the overall function of the system, and you can underscore necessary. That's irreducible complexity. Behe gives this example of this mousetrap in that you cannot remove one single part of the mousetrap and it still works. If we take that same idea and we apply it to biological systems, we see there are biological systems that are the same way. So thinking about the mousetrap, thinking about irreducibly complex systems, is a car an irreducibly complex system?
No.
Why is it not an irreducibly complex system?
Take the radio out or not.
There you go. You can take the hubcaps off. There's a lot of things on a car you can take off. So a car in and of itself is not an irreducibly complex system. What about the human body? A little bit tougher. So the human body is not either. We can lose appendages, we can lose organs, we can lose a lot of things, still function. We can lose our hair, we still do good. So a body, the big system of the body is not irreducibly complex either, but there's parts of the body that are, and there's parts of the car that are. You know, you take a tire, I don't think there's anything that you can take out of a tire. Where's Jesse? There he's back. Can you take any part of a tire out and it still be a tire that functions? I got him with a mouthful.
Firestone tried that 30 years ago, and it didn't work out.
Okay, so a tire is an irreducibly complex structure. So that is what Behe said. Another example he gives is flagella. And flagella is these little whip-like structures that are on the surface of a lot of bacteria. And this is how bacteria propels itself through fluids. And it runs along and it wiggles these. And you've seen, if you've ever taken science and you looked in the microscope, you see the little things wiggling across, swimming through the water. And this is what propels them, is flagella. But flagella is a very complex system as well. This is what flagella looks like. So that's where it goes through the cell wall. There's a 2-layer cell wall there. It has a bushing. It has a universal joint. It's a whole lot like an outboard motor. It's got a rotor. It's got a stator. It powers itself by an acid gradient from one layer to the other layer. The acid passes through an acid gradient. That's how it generates its power. It's not off of ATP like everything else. So it has a very special way it generates its own power. There are there's between 30 and 40 unique proteins that make up this flagella. They're not used in anything else inside the bacteria. They're very specific proteins just for this. So how do you build that one step at a time? That's an irreducibly complex system. You take the little whip off, it's no good. You take the rotor out, it won't go. You take the stators out, it wobbles and it tears itself up. It's an irreducibly complex system. That's on a microscopic scale. This is the work that Behe and his colleagues do. On a very microscopic scale, on a very, very cellular scale, on a biochemical scale. Darwin's evolution says that complex systems arise through these numerous successive modifications for generations and generations and generations. So let's say this even starts. Let's say all of a sudden this bacteria develops just the flagella and it's stuck out there. But there's no motor yet. We're going to build the motor later part by part. So there's just the flagella out there. That's not helpful. In fact, it's a hindrance. Now you've got something that's hanging out there that gets tangled up with other stuff and it does you no good. It's a hindrance, it's not a benefit. So if you're a bacteria and you have a mutation of a flagella hanging out there that doesn't do anything, that's not an advantage. Darwin says it has to be an advantage. If you started on the inside, let's say the bacteria just developed the rotor part. What good is the rotor without any of the other parts? It can't give you any propulsion. In fact, it's just extra weight. And weight's a big deal in biological systems. That's not an advantage to have the extra weight there. So it's impossible to get to a fully functioning flagella piece by piece by piece. The other thing that's interesting about this is it can rotate at 100,000 RPM, come to a complete stop, and in a quarter turned, reverse back the other direction at 100,000 RPM. Just by chance. Just by chance. But flagella is not the only thing. We see this in a lot of biological systems. We see it in psyllium, and Kim may help us more on some of this stuff than I could do, but the cilia in our throats that works mucus up and out is an irreducibly complex system. The blood clotting cascade, there's all these chemistries and proteins that are involved in blood clotting, and it's a series of steps that has to all be in place. You can't remove one single step out of the blood clotting cascade and still get blood to clot. Isn't that right, Dr. Clark? So that's a very complex system. Our adaptive immune systems. You know, you can't the T cells and things that react to pathogens. You can't just build those systems step by step by step. DNA and RNA replication is a huge one, and this is a big one. You know, how do you form a DNA strand step by step by step? More than that, how do you form the mechanism that causes DNA to split into half during meiosis? You know, it takes place when you in the reproductive cells where the DNA becomes unwound and splits off into two. You know, how do you? That's an irreducibly complex system. You can't take parts and pieces out of that. The golden ratio is another one, and we'll talk about this one in a minute. Is an irreducibly complex, and it's an interesting design scenario. And then the eye, and we'll talk about the eye. Well, isn't that a beautiful eye? I spent a lot of time looking through eyeballs on Google, and I picked that one. I thought that was a pretty good eye. Anybody heard of the golden ratio? Oh, we've got a few know what the golden ratio is. So the golden ratio is a number, 1 to 1.618. And it's a ratio that we see throughout nature. It's in everything in the world. We see it all around us. We see it in art and in architecture. And it's this ratio that of different pieces to the whole or different pieces to other pieces falls within this ratio of 1 to 1.618. Human faces that we deem in society to be beautiful fit this 1 to 1.618 ratio. They fit this golden ratio. We see it in flower petals, and we see it in leaf configurations. We see it in shells. I've got some of these are really cool. The ratios that these, I'll let you pass these around. These are all meet that ratio. Come on. This spiral here. You can pass that down and pass it to the back of you. That spiral inside that shell, if you'll look at that, it meets that same ratio. The universe is laid out that way. The cochlea in your ear, the pattern when you see the rain pattern when a hurricane's about to come on shore, that pattern of the outward bands meets the 1 to 1.618 ratio. The distance from your finger to your wrist in relation from your wrist to your elbow meets the 1 to 1.618 ratio, the golden ratio. Your navel, from your navel to the ground and from your navel to the top of your head, those two ratios meet the golden ratio as well. It's everywhere, all throughout nature. We see it in starfish. It's present in starfish. It's present in the fins and the eyes of dolphins. Like I said, the cochlea in your ear. Ants, the configuration of the ant's body. A lot of insects, honeybees, are laid out in that same golden ratio. Like I said, it's everywhere. and the universe itself. Now, pray tell, how did all that just happen? Here's the interesting thing, and this gets very interesting because it touches on both mathematics and aesthetics. Things that we view are beautiful meet the golden ratio. And there's a lot of things in nature that meet that. Beauty is a useless entity in Darwin's evolutionary theory. Beauty has nothing to do with anything. Beauty is one of those things that you can't explain, that a Darwinian can't explain. It has no point to our survival. And so beauty is a big thing in that golden ratio. I'm going to stop right here for today. Any questions? Any comments? Any thoughts? Come on now, I like people to talk.
I'll bring up something. Have you ever heard of the tardigrade?
They're ancient, yeah.
And they get high levels of radiation and stuff like that. Thinking of a perfect design just resonates.
Yeah, tardigrades,
yeah.
Water bears.
Yeah,
They're called water bears.
Yeah, pretty cool. And there's actually like some 100 billion of them for every one of us.
Yeah.
And
Well, believe it or not, my biology professor years and years ago was a tardigrade specialist.
Oh, really?
That was his focus. That's what he studied. So
yeah, they're pretty cool.
So you had to like water bears to be in his class. So yeah, they are. There's a lot of things like that. You know, there's so much stuff in nature that we just look at and we don't see the design. We don't give it the thought. You know that. You know, when you start looking at things, you know, when you're walking through a field or whatever, pick something up and look at it. You know, you just think, where's the design of this, and could that just happen by chance? My brother was a veterinarian. He was an interesting man, and he was like a little kid in a lot of ways. He would find something neat or cool on the ground. He'd pick it up and he'd carry it with him for 2 or 3 or 4 days. And I'd say, what are you doing with that? And he said, I just carry it and just look at it and think about it, and then I'll throw it down and I'll pick something else up. You know, a piece of bent wire, you know, or he had a knot one time. I said, that's cool. He said, here, you can have it. So I've still got it. It's a knot, a wood knot. But do that over the next week. If you're out mowing your grass, pick up a dandelion. I hate dandelions. Steve.
I was just going to say that this is, it makes more, I don't know if it makes more sense, but it's good to watch it again. If you want to watch it on the, what do you call it?
The video, yes. Thank you.
You've done a good job putting that on there.
Yes.
The first one's a little iffy, but the second and third one.
Yeah. Good. Yeah, and I'll remind y'all that, you know, you took the initial survey, and then there'll be a survey just like that at the end. There's a few questions that are different. If you've not attended all of the classes except for one, or at least watched them online, I can't use your data. And so your surveys I've got to just throw away. And that becomes a real problem for my research from a data set standpoint. The more of you that can certify on that last survey that you've attended all the classes or all of them but one, by one means or another, really be helpful. So if you miss, I'd appreciate it if you'd go on and watch those. But are you all enjoying the class? Is this boring? Is it good? Biff says this is yes and this is no.
Very interesting.
Okay.